we only have 2 chapters left, which is good because, let me see here. Let's take a peek at our calendar. And that's pretty much what we're looking at. So, we are here. Oh, there's Katie. That's the 11th. I don't know if anybody even uses the calendar. I find this handy just to see when things are happening. So we're here. We finish up this week. We start, like I say, we're starting chapter 22, and then we'll kind of finish that all up and everything. Like chapter 22, and maybe start taking a peek at chapter 23 here. Maybe not. We'll see how it goes with Thanksgiving being in the way. Um, and don't worry, I'm not. Unless you guys want, like a take home project or something for a week of holiday, but I usually don't do that. Like, here, go and make this nice 5-page report. No, because then I have to read. No, I'm just kidding. We don't really. I don't know. It'd be hard to do reports, I guess. They'd be boring. Definitely boring. What would we talk about? Capacitors and inductors. Ugh. But no, that's kind of what we're looking at. I signed the chapter 21 homework yesterday, and I signed the chapter 20 quiz, and then I made a makeup quiz. So if you are missing any quizzes or something like that, and you want to pop up your grade or something like that, you are more than welcome to take the makeup quiz. It's kind of just a compilation of the previous quizzes, and I'll use that as a grade thing for your quizzes. I don't want, I mean, you guys are all doing actually really well in this class. I'm impressed. I'll be honest with you. It's going very well. So, but today we're going to start taking a look at, actually the next 2 chapters are pretty exciting. Well, for me, because up to this point, I mean, really, what have we been? We've been working with the components, finding out their properties, how they work, and that kind of thing. But we haven't really done anything with them. And now the next 2 chapters, we actually start examining what the heck do we do with these things, and it'll be fun actually. but but I have a couple of labs that'll go along with it, so they'll probably be the more tougher labs, if you will, just because we're actually examining, the properties of these components, the capacitors and inductors, and of course resistors. Um, and we'll have a couple more labs that'll reflect that. So expect the lab circuits to be a little, I mean, not much more, not really, but a little bit more complex. The way we analyze them and what we're going for. We're going to target specific frequencies, and we're going to achieve desired effects that we wish to have. And at this point, we have pretty much all the tools we need. So let's, but yeah, that's our schedule. We still got what, the rest of this week, and then the following week. Then we take a week off for Thanksgiving, and then we come back for a full week, and then it's finals week. So really, that Monday right there on December 7th would be our last meet day. I figured we'd probably just meet online here and then do like a review for the final, and then whatever day they have us, probably Wednesday or something, whatever day they have us set up for the final. And I mean, I could just post it up and we'll go for a couple of days or whatever, and then you guys take the test, and that'll be that. And then we'll be all off until the end of January, basically. So there is, there is one thing. We did skip the one chapter because I just felt it wasn't as relevant, the Transformers one. But he does refer to a couple of terms, like in the later homeworks, and I just wanted to clear up any misconceptions with that, with what he was referring to. He talks about, he talks about real power and apparent power, and what are the differences with that. And for apparent power, they like to use, it's still the power formula, but they like to use the I square over R. So you're basing it solely upon the current. Whereas we usually measure power, like, P is equal to E times I, and we measure that in watts. Now, when they talk about apparent power, they don't put watts, because watts is actual work being performed, right? It's being done. So if we had, something simple like your lamp or something like that, where you have like a 60-watt bulb, and when it's glowing, there's 60 watts of power being consumed at that point, right? It's actual real power. This is happening. Now, the apparent power, just for a good example, you have your your electric panel, okay? And in there, you have a series of breakers, 15, most common ones are the 15 amp and the 20 amps. Excuse me. But that doesn't mean that when you have like a 15 amp breaker, that your house, the power you're using is always drawing 15 amps, right? You could be using 6 amps on that particular circuit, 2 amps, and etc. But you have 15 amps of power available to you. And so when they rate that, you'll see this on electrical equipment from time to time, specifically like transformers and basically delivery type equipment, where it has a VA on it, which means overall, how much power can it deliver? So that's an apparent power. So they put a stamp on it, the V, it's capital VA, right? Voltage, amps. But you will see that largely, like I say, on delivery equipment, transformers in particular, because that's typically what we use to deliver, but other sources as well would have that. So when you see that in there, I noticed in the last chapter homework, you did refer to that a couple of times. And so I just wanted to make sure you guys understood what he means by that. We actually, and a couple of the other classes do a much better job of going into it. Like in 150, you examine transformers in much detail. Actually, you'll start looking at all types of coil objects, if you will, like motors and transformers and whatnot, where you're looking at very large coils and examining that. So it does it much better. And it's the same with the very last chapter in this section, the chapter 24, I believe it was, where he examines like residential electricity and stuff. Then we have a whole class for that. And I thought, well, it's nice to gloss over, but it really doesn't have any bearing, if you will, on what, we're doing inductors and capacitors and start examining residential electricity. But so that's the reason I skipped those 2 chapters. But in any case, I'm rambling and babbling. So let us take a look at today's topic. All right, here's our new topic of the week: resonance. And we have series resonance, parallel resonance. What is it? So if we take a gloss and see what he's talking about, we're only going to go, we're taking our time. This is the next 2 chapters. We're taking our time. We're going to really examine these. These are the most important 2 chapters out of everything we've covered so far in this little mini-mester. So today we're going to take a look at what is the resonance effect, series resonance, of course, parallel resonance, and what resonant frequency is. And there's a nice little formula. And notice it's a little odd, right? And why we have that inductor and capacitor inside of a square root symbol down there like that. But we're going to take a look at that. And then we're going to go up to right about here where, remember Q, charge, capacity of charge, okay? So we're going to look at the Q factor resonant circuits, and then we'll stop, and then next Monday we'll pick up and pick up the rest of that. So essentially this whole chapter is looking at the resonance effect of circuits. So what the heck does that even mean? So let's start off with a couple of general statements here and by now we've observed this, right? So we know that inductive reactance, as we increase the frequency, it drives it up. It's a direct relationship, right? Straight in the formula. But we also know that capacitive reactance is almost like the opposite of that, right? So basically, as the frequency goes up for capacitors, the reactance goes down. So almost opposite, right? They do opposite things as far as effect goes. So when we look at this, right? So for any inductor capacitor combination, there actually is a specific frequency where what they call like a balanced circuit, where the reactances are equal. So the inductive reactance and the capacitive reactance are the same. So if we said like X of L was like, say, 1K, okay, then X of C would also be 1K. And at that specific point, there is a balanced circuit as far as, actually for quite a few things, as far as power goes, that's the optimal point for this particular circuit. I mean, at this point, we've just been studying, properties of these components and such, and they do have limitations. And if we are to overdrive these type of things, the reactions are somewhat erratic as far as, the signal output that they have. And with anything, that's not an optimal thing. Typically, when you go for circuits and whatnot, you're going for efficiency. You want efficiency, right? You put power in, you're going to lose power by driving a circuit, if you will, but we want to lose as little power as possible. So, but they call this effect, it's called a resonance effect. And there's actually an extremely long answer, but it's a mathematical answer as far as what we're achieving. But for us, we're going to, as far as what we're looking at, okay, and remember, yeah, these are opposite reactances, the way inductors and capacitors, work when you have a sinusoidal or similar type signals, an oscillating signal, if you will. As far as their reactions to it are opposite, like we've seen in the first statement, as frequency goes up, this goes down and vice versa. Oh, I swear. But anyway, so at the very bottom statement is our most interesting one. See that? Where we have X of L equaling X of C. And then when we do that, the frequency that's a resultant of that, right? So when we do this, and based on the formulas, right? Because we have frequency right in there for the reactances, right? The 2 pi FL and 1 over 2 pi FC. So we have the frequency right in there. So when we do that, and this is balanced like this, that particular frequency is our optimal frequency for the value of components that we happen to have. Now we're going to take a little look at what goes on here, if you will. So here's a little block diagram, and I like how he does this. So our formula, if you will, where's it going? Yeah, see. So our formula, you see how we have a little F sub R? So that's resonant frequency. And what is it equal to? Well, you would put in, it's a fraction. It's 1 over 2 pi, and then it's the square root of L and C. So your values of the inductor and value of the capacitor are both within inside there, not the reactive value, right? We're not using the X of L or anything. We're actually using the straight, Henrys and farads here. And so in this particular case, the 1,000 kilohertz is the optimal signal. And you can even see it in the wave shaping. What are we looking for? We're looking for magnitude output. And so at different frequencies, the way your signal is, I mean, notice the very top one here at like the 500 kilohertz, the way that signal is all like really rounded. So what happened is it has a clipping effect. So we actually are experiencing power loss because it's not a balanced circuit. So where the power loss in that particular one is you lose the magnitude, so your voltage is not as high as it could be. So in this case, we look and see that the 1,000 kilohertz is the optimal, and the other way around. So now we go down in the frequencies, and yeah, we're starting to get our magnitude back, but now we're losing in the actual circuit, if you will. So, but both cases, yeah, we do have power loss, and with anything, we want to minimize that as much as possible, and that is why we do something like this. And we'll do a little something where we can drive it up and down and actually observe this effect, because this is very interesting, and this is what they do with circuits. And largely, you could say these are for communications ends, and that's not like all communications. And in these days, we experience that a lot, right? Not only are we dealing with like radio frequencies and whatnot, but now these days we have, pretty much most of the machines out there, if we go into these factories, they're wired up for internet or they have Wi-Fi, even worse, right? So we're right back to dealing with radio frequencies. So some point, depending you're in your career, you probably will run into things where this will be good information to know. So we'll take a look at this. So we take a look at series resonance, which will be a little different, of course, than parallel resonance. I mean, we're still going for the same effect, if you will. So our first statement, we state, right, at resonant frequency, the inductive reactance and capacitive reactance are equal. Okay, so they'll have the same ohm value. So in a series AC circuit, and at this point we've seen, right, how the series circuits versus the parallel circuits and what these components will do. But in a series AC circuit, all right, the inductive reactant leads by to 90 degrees. And we, of course, the zero reference angle of the resistor. Resistor just provides opposition. It does not affect the phasors. And we know that the capacitive reactance lags by 90 degrees, right? I know we've seen this on the scope. So a good statement to make is that X and L and X of C are 180 degrees out of phase with each other. Okay. And that's an interesting thing. So if we were to have a purely XL and X of C, you would almost think that between the two, it would bring them to a resistor type of phasor, right? But depending on our values. But so the opposite reactances do cancel each other out completely when they're equal. Interesting, right? So again, and then we have a balanced circuit where now we're dealing with just on the resistive part of the phasor diagrams. And like I say, this is an extremely balanced circuit. We don't have any leading or lagging typically. Anyway, so here we see a symbol. So there's your inductor symbol, right? Little coil. Here's our capacitor. I don't know why they're drawn so strangely. It's kind of weird, but anyway. So here is this is our new formula, kiddies. So resonant frequency, right, F sub R is equal to 1 over 2 pi square root of L times C. And that's a straight inductor value, like, yeah, C says in Henrys, and a straight capacitor value in farads, and whatever our crossover frequency happens to come out to be based on the values we have. Let's take a look at a little circuit. Now, in this particular circuit, it has a resistor drawn there, and I'm going to basically make a point here that there's not an actual resistor. And you'll see how it's got the R sub S symbol, and it's a real low value, 10 ohms. That is the actual resistance of the coil itself, the DC resistance. Remember in a one lab when we took our coils and we measured, with no energizing, what the resistance value was, and it's usually really low because it's just a big coil of wire. So that is what that is. So in reality, we just have an energy source, inductor, and a capacitor. But for like a truly balanced circuit, you do have to observe all properties. So we would have to have drawn in, what is the actual value or resistive value of the inductor itself. See, yeah, the only opposition to current is the coil resistance. And it does, unfortunately, provide us a slight limit on how low the series resistance in the circuit can be. Because no matter what, we're always going to have that actual resistance of the coil. But more of interest for us is this graph on the side. See the parallelism here? And you'll notice the inductor nice and smooth, and unfortunately the capacitor on opposite ends, it tends to start acting strangely, if you will, and that's the charge discharge effect. But you notice right in the middle, if we have the optimal frequency, that it's nice and steady state even. And then we actually can draw parallelism between the two, and this would be a balanced circuit. And we can, we look at it, yep, X of L, X of C, both being 90 degrees out of phase. We have a resultant phasor individually. It's like, okay, what's our overall response here? And then we set the two to equal, and they would be extremely balanced right in the middle there. So both components aren't being overdriven or underdriven. They're being driven optimally to deliver without distortion, mind you. There's so many effects that can happen to these particular circuits when you have like a sinusoidal go in, that achieving this actually helps a lot. I know this is all new stuff, but at this point I feel, we've been going through the with the components and doing really well and looking at these, so I know we're ready for this now. So let's examine a particular circuit for this. And remember that R value is the R value of the coil, the inductor. And we look at what he calls the resonant rise and the voltage here. So we got voltage across the inductor, voltage across the capacitor. What's our feed in? We got a 20 volt, 5 kilohertz signal, series circuit with 5 amps throughout. So we look at our Ohm's law statements here. Notice we're balanced, right? So we get the same voltage drop across each. So if we do a KVL statement, like he does on the bottom here, that should balance out and equal to 0. Because essentially, remember, these are both 180 degrees out of phase with each other. So they're on opposite ends, but they both have the same magnitude going on there like that. There we go. And taking a look at a couple of other circuits with that. Again, notice, even between the two, we pump in, we got different values going on here and whatnot. But because we are optimal, right, we've set it up where these guys actually will equal each other. If we were to do the X of C and X of L, we would find that both of those are the same. And of course, we'd have to have, and that's that should be our optimal frequency for this particular thing. And the way they measure that is by the Q value of these particular circuits. That's why we'll end this discussion. We'll talk about the Q value here. But it's the capacity of charge and what it's capable of. Because essentially what they end up doing is, if a design engineer or whatnot was looking for a particular circuit with a certain Q value, he would go ahead and plug in. It's like, okay, I need this Q value of this for this particular operation here. And then would find a very similar circuit to this. And they do that. I mean, why reinvent the wheel, right? If you have these things, so you just use what's there. But in both cases, when we do this, like I say, we'll have the similar, well, we should have the same voltage drops because they're equal as far as reactance goes. So we go through and we actually did like X of C is equal to and X of L is equal to, we would find the same reactive values on both. And the same with the other circuit over here as well. And even though we're dealing with a much different magnitude, basically, and that's just because, see, notice we have the same energy source here, boom and boom. However, we do not have the same value components. Now notice another thing there too is the ratios, right? So down over in the first circuit here, we had a 1 microfarad capacitor ends up being equal with a 1 millihenry inductor. But over on the other side, and it's still a ratio if you look at it, the 4 millihenry inductor being equal with a 1/4 microfarad capacitor. But it's just an interesting thing to note when we achieve these balances, if you will. And what happens? So when you pump in the signal and we look at the output of this thing, we should see a nice, smooth, steady sinusoidal coming out, no distortion and whatnot. And an interesting thing, an ideal world, if I drive it down, I shouldn't experience distortion. If I drive it up, and by driving, I mean by the overall frequency, I shouldn't experience distortion. But unfortunately, in the real world, yeah. And it'll come in different ways. The distortion could be actual noise effect on it. It might be a ripple on the overall magnitude of the signal. It could be a change in the way the frequency is coming out, and whatnot. It really depends on how the components are reacting. But if we look, so we see, what is our table here? So we have a balanced circuit, right? The 1 millihenry and 1 microfarad. Go through and do our math. So if we have these two components, and see, that's the thing, right? The components essentially dictate what the frequency will be. So if we pick these particular ones, we know we want a 20 volt magnitude, but now what frequency am I going to go at? So plug it in, boom, 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 and you see, ideally it would be 5.03, but in reality, we'll use the 5. And if we were to graph this, we would see in our response, right? The optimal response of this particular circuit is 5 kilohertz. And later on, we'll see why we want to know that. Why would that, be of importance? And that we begin to fall out greatly. And as we go higher and higher, this thing's response just becomes crap. You wouldn't want to use the circuit. But at this, you have maximum power effect. This is extremely stable circuit, and we could use that at that frequency all day long. At others, you can see as we go lower, it starts to fall out. We go higher, it starts to fall out. This is where you want this. And that's the series effect. And I mean, we expect what? Similarities in a parallel, but slightly different in the way that the circuit handles this, right? So when we have the L and C in parallel and we set them equal, the reactive branches are equal and opposite at resonance. So you would think they cancel each other out to produce a minimum current in the main line, okay? And since the current is minimum, the impedance is maximum. It's an interesting thing. What changes in parallel circuit? The current. What changes in the series circuit? The voltage. So in a series one, what are we looking at? We're looking at voltage magnitudes. So, all right, our current is set, but the voltage magnitudes are of the most importance, because as we drive up, based on this graph here, okay, notice our magnitude also Got 5. Look, we're driving up nice and high, but look at our power loss here. So as we drive over or drive under, we experience an extreme. I mean, really, after you get up to about here, your power loss is insane. And so you would not want to be running this circuit either way. Okay. All right. Sorry. So, and formula is still the same. So resonant frequency formula, okay, it's equal to 1 over 2 pi square root LC. Ideal world, we're not going to have any resistance, so we wouldn't have the little inductor resistor on there. Okay, real world, well, there's approximation methods, and right now we're dealing with the first approximation, which is, ideal world. We don't experience bad things, if you will. All right, so let's examine this. So here, what do we have? Our resonant frequency is set at 1,000 kilohertz. Our voltage, look at that, 300 microvolts. Why bother? No. So in this, we have our capacitor, we have the inductor, and yes, we have the actual DC resistance of the inductor in there as well. Okay, because that minimizes how far down we can go as far as resistance goes. Excuse me. So what are we looking at? So we see our crossover frequency here, okay? And what he's measuring, so you see the line current at a minimum at this point, which is almost like a reverse effect of the series if you think about it. And on this one, this is the impedance overall, right? How much opposition does this circuit have? So you can see, look at that. Oh my God, it's so small, 0.00133 microamps. Okay, you would almost think it's non-existent, but for the circuit, it is there. Okay, I mean, look at what we're dealing with as far as values of these components. You got a picofarad and you got a microhenry, which are extremely small, but and a lot of times when you look at the inside of these electronic assemblies and whatnot, and you see these really small components, well, this is what's going on here. So if you wanted to build a particular circuit that had an extremely, and notice, I mean, look at that. So from these two, and remember now the values of these things being so low like that, but look at my overall impedance value here, 225,000 ohms or 225K, right? Out of that with, I mean, 300 microvolts, and we're dealing with microamps, and yet we've got such an extremely high resistance. Interesting. So that's cause and effect of the parallel. The parallel is an interesting little animal. And if we were to measure it, see here, we look at our inductive curve and our capacitive curve. And for this particular circuit, we could say that the 5 kilohertz signal is our optimal here. Because notice, as we go lower in frequency, the inductance starts to kick up and our current starts reacting normally, and we get the 3 amps here. Or the other way around, as we drive the frequency up much, much higher, okay, our inductance goes way, way down, but our capacitance starts to increase where we drive up as well. So our optimal here, where we're almost at 0 amps, like that. Interesting, right? Almost at 0 amps. Anyway, but that is the particular response for a parallel resonant circuit. And needless to say, how often do you see parallel resonant circuits out there? Not very often. They have a particular use, but anyway, we'll get into it. So our bottom line, so really when we look at this, what are our takeaways from this so far are these two statements right here, these two formulas. The first thing that we're going to want to do, we hear resonant, okay, we want to build a resonant circuit. So the first thing we have to do is this. we set X of L to equal X of C. And then we will find what our resonant frequency is here. And then we use this formula where F sub R, right, resonant frequency is equal to 1 over 2 pi, and now it's the square root of L times C. So whenever you want to hear, whenever you want to set resonant frequency for a particular circuit, these two statements are really what you want to do. And then do the juggling with the component values and whatnot. You know, you want to find good off the shelf stuff and whatnot. And I mean, granted, if you were out there, like say, you know, building these things as an engineer or whatnot, you can use any values, but bottom line comes, it's cost, right? So you want to be able to use as much off the shelf parts as you possibly can because they tend to be cheaper. You start getting into specialty builds where, you know, this company doesn't make these parts that often, and now you're going to be one of their customers for that part. Yeah, you're going to pay for that. And of course, that cost passes on to your customer. Yay. So, but yes, these two statements are two huge takeaways for today, that the X of L is equal to X of C and our resonant frequency formula. Okay, I mean, really, this is like the culmination of everything that's gone before. We looked at cause and effects of the series and the parallel, and you've seen that for the parallel, an extremely high impedance factor that we end up getting as a result of that. And then the series and what it does. So ideally, yeah, series resonance circuits will probably be the more common that you would run into out there. And the parallels, not too often. But so we'll finish today with this guy right here with the Q magnification factor of a resonance circuit. Sounds scary, doesn't it? Ooh, so much. But so the quality of the resonance circuit, oh God, and sharpness of resonance is indicated by the factor Q. And Q, like I say, usually is, we use Q for measuring charge or capacity to charge. You could put a Q factor on anything. You, in the wintertime, walking across a carpet, okay, building up a static charge, you would have a Q factor, because now we would have to figure out how much charge you're accumulating, right? When you go up and, like when you were a kid and you zap your little sister in the ear, or you hit the family cat in the nose with a shock. But if you think about it, you're building up a charge. You are now, what are you? You are like some kind of capacitor or inductor building up a charge by walking across the carpet. You would have a Q factor, and we could mathematically go through and find out what your Q factor is. You know, it would have different things, you know, based on what kind of clothes and shoes you're wearing, right? Temperature, how much free ions are in the air, and how many electrons you're picking up off of the carpet, if you will, and so on and so on. But so when we look at Q factor, that's really what we're looking at, the capacity to charge, just putting in like real man terms for you guys. So the higher the ratio of the reactance at resonance, okay, if we examine like the series resistance, the higher the Q. And the sharper the resonance effect. So what he means by that sharper, so from that graph, here, let me go back here. Hold on 1 second. The sharpness. So when we look at that graph, right, so we see the overall peak magnitude of this bad boy is at 5 kilohertz here. So the sharpness would bring this thing to like a pivotal point, right? So this would be perfect. That's what he means by sharpness. Ugh. Yeah, I get to do that. All right, so the sharper the resonance effect. The Q of the resonance circuit can be considered a magnification factor that determines how much the voltage across the L or C is increased by the resonant rise of current in a series circuit. And it's a way to quantify your particular circuit, because because it may be, I mean, when you look at it, all right, so I set my frequency. Let's say I'm dealing with a particular frequency and I build a circuit to respond to that. So really what they're saying here, because when you plug in that formula, there's actually a particular combination where you could, I mean, you could come up with several different types of inductors, capacitors to fit the role, right? But ideally, there would be one value of each that would really work best with that particular frequency. So granted, yeah, all these ones we could play like combination games all day long. It's like, all right, find out how many combinations of inductors and capacitors ideally run at resonant frequency at 1 kilohertz, and then plug away. You'll find quite a lot, but there are particular ones that perform extremely well with that. And that's really what he's talking about here. Okay. Because it'll determine how much the voltage across the L or C is increased by the resonant rise of the current in the series circuit. So really it's the way the components are responding, if you will. And so they reach the stability point, and then our Q factor, our capacity to charge, becomes optimal. So like in this case, so we look at our circuit and notice what he's using, okay? Our Q in this case is going to be our X of L, all right? So the reactance of the inductor divided by the actual internal resistance of the inductor, and we come up with 31.6. All right, what the hell does that even mean? Okay, I'm glad you asked. So, so let's take a look at this. So see how this is drawn out. All right. So we have two different circuits, okay, both, like I said, two different values of components. Both are optimized to run at this frequency, having, a resonant frequency of 5 kilohertz. But look at the difference between the two. So on this side, it's our red, right? Look at our response there. And this side is our blue. And granted, they both are resonant at 5 kilohertz, but the blue one responds much, much better. See that? Nice clip, pointed, and really, really will become very, very unstable, really, really fast at anything other than 5 kilohertz. The red one does better, see that, at the lower and higher frequencies than the blue one, but that's not our desired effect. We want to have the best circuit that we can have for that particular frequency, and a variety of reasons. It deals better with the signals. You have less chance of crossover distortion and things. There's like a variety of effects that we tend to help eliminate by having the circuit built like this. So see the difference, and even though, okay, both are optimal for the 5 kilohertz resonant frequency, but look at the difference in the Q value. The red circuit, it has a 7.8 Q value, and the blue circuit has a 32 as a Q value. So much higher, deals much better as far as stability is concerned. And that's why we would look at something like that. Day to day, do we really care? Nah, this is more of a design aspect, or if you will, but it is something to note. And in a way, you could even check like somebody's work, if you're dealing with an already built assembly, and it's like you see red circuit when you should see blue circuit. Obviously, that engineer either A, didn't know what he was doing, or B, didn't really care. In either case, now you have to deal with his junk. Ugh, awful. But so this is just merely something to observe and whatnot. So noting like this does occur, and yes, there are more ideal ways to do this and whatnot. And so when you're playing with your values, you would almost think, well, let's go and deal with this and see what particular Q value I can achieve overall, and then set my components based on that. So if I were plugging through, and let's say I had even a list out, and I could say, well, these all respond well to the 5 kilohertz, but this Q value is much, much better. So I will go with that one. All right. Oh, that's it. So that's it for today. There's no, now, oh, let me stop. Let's stop sharing this. There we go. So there's no homework from this yet. So we are dealing with this at this point. So like I say, we assigned the chapter 21 homework and a 20 quiz, and I made them do next Monday by midnight. And then tomorrow we'll meet for lab, and I'll hand out the last series parallel, our LC circuits for us, our LC circuits. And at that point, we've done like all the common stuff to do with these components, and you should be comfortable, dealing with the equations and what kind of signals we're going to see. And obviously from this point, you realize that the parallel circuit is not as common as the series one and so on. And I mean, there's even like things later on, like why do you see this one instead of this one over time? And a lot of times, believe it or not, it's cost. It can be cost. RC circuits tend to be more common than RL circuits simply because of the cost factor. I mean, getting like those little capacitors you have in your kits, the little round Mylar guys or Mica, whatever the heck they have in there. Those are a lot cheaper than the inductors. And the inductors, I mean, they still have to spin so many turns of coil around inside of there. So that process, even though it's automated, tends to be more time consuming. So cost prohibitive. So when you look out there, why do you see so many more RC circuits than you do see RL circuits? That's part of it. The other, inductors are electromagnetic. And believe it or not, when you deal, I mean, even though you could set yourself optimally and this and that, overall, the inductors do have a certain amount of EMF to them. So when you build a circuit with them, they have a tendency to be able to distort other signals. So you could have a crossover. I had, this is years ago, we had a particular board we had in our machine that had a pre-built oscillator. The thing was actually pretty good sized, but it was right on the board, the PCB printed circuit board. They and it worked fine. And, the engineers went through and designed it and whatnot. But what happened was they changed the board, because after you do so many revisions on a board, you do rework on them, and at a certain point you go, well, now it's time to redesign this board with these rework changes in there. And in that process, it changed it a little bit. So when this oscillator would start kicking in, the magnetic waves would start kicking out. It was actually distorting signals on that board. And so we had to go through and build like some shielding on it and whatnot, which was goofy. But inductors tend to have a wave effect, if you will. So there's a certain amount of radiation around it, right? So capacitors don't do that. So stability wise and cost wise, you will see a lot more RC circuits out there than you will RL circuits. But anyway, I'm rambling. I'm sorry, guys. But yeah, that's our schedule. And if you have any questions, I did do something like a makeup quiz. If you missed any of the quizzes or whatnot, and you want to pop that in and let me know, and you can, anybody's welcome to take that makeup quiz. But I mean, if you have everything, why bother, right? But that's their due dates, and by next Monday. And then we'll meet tomorrow for lab, and then and we have the next week to go through, and then we take our little break with Thanksgiving. But we'll start our next couple of new labs, if you will, the more adventurous ones, where we're actually doing some of this stuff. It'll be a lot more fun, actually. And I went through yesterday, and all of our speakers are in good shape. So we'll be able to definitely do my last experiment that I wanted to do. Oh, so noisy it's going to be that day. Oh, but it'll be fun. We're actually going to make these things do something finally, huh? So, but that's what we're looking at. We're very, very much on track to the point where now we can take it easy. See, these two chapters coming up, like this chapter 22 with the resonance, and then the next one are, for in my eye, the two most important takeaways out of this whole thing. So, actually see cause and effect of these components and what we can do with them, or what people do with them. But that's it. So we'll meet tomorrow for lab, and like I said, I'll hand out the series parallel. There's not a particular due date for those. Sooner better than later, right. But I see everybody working in labs, so we'll I don't know. We'll see when we get them all done. But don't take too long. I don't want that to be, a factor. If any of the questions are stumping you guys, always come and see me. I mean, always come and see me. I am more than happy to work with you and come up with our solutions and such. But yeah, that's what I have today. So if you have any questions, and if not, then let's get the heck out of here, and I'll see you guys mañana.
See you tomorrow.
All right.
See you, Tom.
Hey, buddy.
See ya.
Bye.